This lecture is validating regression model assumptions. The lecture objective is understanding different types of residual analysis and plotting residual plots using Python. Residual analysis, validating model assumptions. First we will see what is residual analysis. Residual analysis is the primary tool for determining whether the assumed regression model is appropriate. So, the residual for observation I is nothing but yi, that is the actual value, and y hat, our predicted model. So, the difference between actual and predicted model is nothing but error, otherwise you can call it as residual analysis. So, yi is the observed value of dependent variable, yi hat is the estimated value of dependent variable. Assumptions about the error term, that is epsilon, we know that y equal to beta 0 plus beta 1x plus error term. What are the assumption about this error term? Number 1, the expected value of error is 0. The variance of error term denoted by sigma square is the same for all values of x. The values of error are independent. The error term epsilon has a normal distribution. We will validate, we will check these assumptions by drawing various residual plots in this lecture. Why this assumption is important? These assumptions provide the theoretical basis for the t-test and f-test used to determine whether the relationship between x and y is significant, and for the confidence interval and prediction interval estimate. What we have done in the previous class, we have done t-test and f-test to test these hypotheses. What was our hypothesis? Beta 1 equal to 0, beta 1 is not equal to 0. So, this assumption can be tested by two methods, one is the t-test and f-test. So, to validate that assumptions, the error about assumption is more important. If the assumptions about the error term epsilon appear questionable, the hypothesis test about the significance of the regression relationship and the interval estimation result may not be valid. That is why we have to verify these assumptions. We will take an example. This example is adapted from Statistics for Business and Economics, David R. Anderson, Sweeney and Williams. So, student population xi 2, 6, 8, 8, 12 and so on. Sales of ice cream is given. So, we have fitted the regression line y I hat equal to 60 plus 5x. So, when you substitute the x value here, this is actual 58, this is our predicted 70. The difference is 50 minus 70 is minus 12. So, 105, 90, the difference is 15. So, this yi minus y hat I says that is the residual. So, this residual have to have some properties. That properties we will check it. The residual analysis is based on the examination of graphical plot. So, we are going to plot that residual, it was in the previous slide, then we have to check certain assumptions. There are 4 methods we are going to do in this class. One is a plot of the residual against value of independent variable x. So, first assumption is x axis we are going to take x value independent variable, in y axis we are going to take residual. The second assumption is the plot of residuals against predicted value of the dependent variable y cap. So, in x axis we are going to have y cap, then y axis we are going to have residuals. The third assumption is a standardized residual plot. We are going to standardize this residual. We know that how to standardize. Standardize, for example, if you are standardizing, this is x minus x bar by sigma, this is the way, sigma or standard error. So, it is nothing but z, it is nothing but z or t. So, we will standardize our residual, then we plot it. The last assumption is normal probability plot. So, we will check these assumptions. The first assumption is when we plot the residuals against x value, so this error, the residuals are plotted this way. So, what is the inference we can get it? Number 1, that it is not following any pattern. If it is not following any pattern, these errors are independent, then there is no problem in the assumptions. So, this one we have done with the help of Python. I have brought the screenshot. At the end of this lecture, I am going to run all these codes, you can verify it. import Seaborn as SNS. Before that we have to import the data set that I will show you at the end of the class. So, SNS dot resid plot. So, this is used for plotting the residual. One variable is student population, that is x value, the y value sales, color is green color. So, we will get this output. So, this was the Python output of residual sales, that is a y predicted value against sales. Y axis is not the sales, it is the residual. It is the residual. Y axis is not the sales because sales will not become 0. So, the one assumption is the variance is the same for all values of x. So, what will happen now in this figure which is given, it is it looking like a rectangle shape, that means this assumption is valid, it is a good pattern. So, what did this graph implies? The residual plot should give an overall impression of horizontal band of points. So, that means the variance, even though the x value is increasing, the variance is same. So, then we will get a horizontal band of points. So, this is the way to check the one assumption that the variance is same for all values of x. Sometime what may happen, when the value of x increases, the variance may increase, that should not be the case. Yeah, that is an example of this one. What is happening? Violation of assumption. What is that? The variance of E is not the same for all values of x. When x is increases, the variance is it is getting a conical shape. So, it is a non-constant variance. This is the violation of our regression model. So, assumption of a constant variance of E is violated if you are getting this kind of shape. If variability above the regression line is greater for larger values of x, then you can get this kind of pictures. So, that is not correct one. Another type of picture you may get it when you plot a residual against x, a curvilinear, this is a kind of a non-linear shape. So, instead of fitting a linear regression equation, it is suggesting that you can try for curvilinear regression model or multiple regression model should be considered if you are getting the plot is in this shape. Previously, we have plotted the residual against x, now we are going to plot the residual against y hat, that is our predicted value. The pattern of this residual plot is the same as the pattern of residual plot against independent variable x. It is not a pattern that would lead us to question the model assumptions. Why this we are going for that one? If there are more number of independent variable, for each independent variable you have to plot this residual. So, instead of going for different independent variable, if you plot this residual against this predicted value, then from that we can verify whether the model is valid or not. So, for simple linear regression, both the residual plot against x and the residual plot against y hat provide the same pattern. For multiple regression analysis, the residual plot against y hat is the more widely used because of the presence of more than one independent variable. Whenever there is more than one independent variable, instead of going for x, we should go for y hat. Then we will go for next residual plot, that is a standardized residuals. Many of the residual plots provided by computer software packages uses a standardized version of the residuals. So, what is the standardized version? A random variable is standardized by subtracting its mean, dividing the result by its standard deviation. Okay, this way z equal to residual I value, residual mean value divided by the standard deviation of the residual. With the least square method, the mean residual is 0 because sigma of x minus x bar is 0. Thus, simply dividing each residual by its standard deviation provides the standardized residual. So, what you have to do in the least square method, simply you have to divide the residual by its standard deviation, that will give you the standardized residual. So, I am showing the Python code here. This is a screenshot of the program. Import pandas as PD from statsmodel.formula.api, import OLS from statsmodel.stats.anova, import anova underscore lm, import matplotlib.pyplot as plt. So, the data set name is Icecream. So, in the independent variable is student population, the dependent variable is sales. So, to get a regression model, reg 1 equal to YLS formula equal to sales is dependent variable tilde student underscore population data equal to df1. So, when you print a summary, so you will get this kind of regression output. So, this says your R square, this says our adjusted R square. I will explain the meaning of adjusted R square in multiple regression. This was for F statistics. So, what say this is, so y equal to 60 plus 5x1, x1 is number of student populations. So, when you use this print ANOVA underscore LM for our model fit 1, you can get the ANOVA table for regression analysis. So, for a residual it is 8 because there is a 10 data set. So, the degrees of freedom is n minus p minus 1, p is number of independent variable. There is only one independent variable, so the degrees of freedom is 1. This is sum of square for student population, this is sum of square for error. Sum of square divided by degrees of freedom, you will get mean sum of square. So, the f value is nothing but mean sum of square divided by mean error sum of square. So, the p value is very low. So, we can say that the model is valid. Next, I will tell you how to find out the standardized residual. So, the standardized residual is S yi minus y hat I equal to S into root of 1 minus hi. Here S is the standard error of the estimate. So, in the previous, this is where MSE is 191. When you take the square root of this, what is the standard error is? Standard error is SSE divided by n minus 2 when you take square root. Otherwise 191.25, when you take square root that, you will get the standard error. So, that is nothing but the value of S. So, you can find out hi equal to 1 by n plus xi minus x bar whole square sigma of xi minus x bar whole square. So, there is an illustration. So, I is there, x is there. We are finding xi minus x bar because this value will be useful for the formula which is in the previous slide. So, xi minus x bar whole square. So, when you now we can divide xi minus x bar whole square divided by sigma of x minus x bar whole square, then you can find out hi. From hi you can find out the syi minus y hat I. From that you can find out the error yi minus y hat I. So, then you will get the standardized residual. So, standardized residual is nothing but yi minus y hat I divided by syi minus yi hat. So, what will happen? When you plot this figure x against the standardized residual, most of the data point is see that between plus 2 and minus 2. So, that means that 95% of the time the data are within the limit. So, this is acceptable. The assumption is valid. We can plot the standardized residual plot against the independent variable x. So, for that you have to use this command influence equal to fit1 dot get underscore influence resid underscore student equal to influence dot resid underscore studentized underscore external. So, you can see what is that resid underscore student, that is an array of, this is nothing but the standardized residual. So, now you can plot student population against the standardized residual, you will get this figure. See, all the data point is between plus 2 and minus 2. So, this assumption is valid. The standardized residual plot can provide insight about the assumption that the error term E has the normal distribution. If this assumption is satisfied, the distribution of the standardized residual should appear to come from a standard normal probability distribution. Studentized residual. Thus, when looking at the standardized residual plot, we should expect to see approximately 95% of the standardized residuals between minus 2 and plus 2. We see the figure that from the ice cream example, all standardized residuals are between minus 2 and plus 2. Therefore, on the basis of the standardized residuals, this plot gives us no reason to question that assumption that the error term has a normal distribution. Next, we will plot normal probability plot. Another approach for determining the validity of the assumption that the error term has a normal distribution is normal probability plot. Many software packages you may see that the normal probability plot. To show how a normal probability plot is developed, we introduce concept called normal score. Suppose 10 values are selected randomly from a normal probability distribution with mean 0 and standard deviation 1, and that is sampling process repeated over and over with the values in each sample of 10 ordered from smallest to largest. For now, let us consider only the smallest value in each sample. The random variable representing the smallest value obtained in a repeated sampling is called first order statistic. Okay. The second largest is second order statistic, and so on. So, this was the first order statistics. So, for the first order statistic, wherein the sample size equal to 10, it should be minus 1.55. That means these values data are coming from the normal distribution. So, for the second order statistics, the value should be, so this value which we got from the table. Okay. Now, we are going to compare the standardized residual values with this table. So, already we have the standardized residual when I equal to 1, xi equal to 2. So, it is minus 1.0792. So, these values we are going to compare with the standardized. So, this value we are going to compare with the normal scores. So, what is happening here? When we look at this picture, when the order statistic is 1, the minimum value is minus 1.55. So, in this figure we have to see which is nearer to minus 1.55. So, this one minus 1.7. So, this is the minus 1.77. Next we have to see which is the least value. From this figure, next least value is 1.07. So, minus 1.07 next least. So, we have mapped this our standardized residual against the normal score. When it is the least one is taken as minus 1.71, when it is 1.55 in the normal score, the corresponding score from our data set is 1.4230. Now, we will see what is normal probability plot. By using this data, we will plot it. If the normality assumption is satisfied, the smallest standardized residual should be close to the smallest normal score. The next smallest standardized residual should be close to the next smallest normal score, and so on. That is why we mapped it in the previous slides. If we are to develop a plot with the normal score on the horizontal axis and the corresponding standardized residual on the vertical axis, the plotted point should cluster closely around a line is 45 degree passing through the origin if the standardized residuals are approximately normally distributed. It is a property of this residual plot. So, such a plot is referred as normal probability plot. So, this was normal probability plot. So, in x axis normal score is written, in y axis the standardized residual is written. So, it is starting from 0, the line is 45 degree. So, all the points are right, it is not deviating from this line. So, it is a clustering around this green line. So, then we can say that this data follow normal distribution. Suppose the data is following this point, this point, this point, it is not going, it is not clustered around this green line, then we can say it is not following normal distribution. This also we have done with the help of Python from SciPy import stats, import stats model.ap as SM. So, we are going to take residual as RES equal to fit 1 dot residual. Then we go for prob plot equal to SM dot prob plot, because SM and all different library which is already imported. See that import stats model.api as SM. So, then figure prob plot dot qq plot when line equal to 45 degree. So, we can say h plt dot title qq plot against residual of YLS fit, then we are getting this. You see that all the points are above this red line, then we can say this normality assumption is validated. Now, what we are going to do, I have prepared this command in Python. I am going to run all the Python codes, then I am going to verify, I am going to show how to get this residual plots then how to verify that it meet the regression assumptions. So far I have shown the screenshot of the Python output. Now I am going to run and I am going to explain how to get the residual plots and what is the interpretation of that. For that, what I have done, I have taken one regression example. File names where I have stored the data is Icecream. So first I will run this. I have run the library. Then I will show what is the data set. This data set shows there is a two variable in this one. One is student underscore population is independent variable, sales is dependent variable. So for this data set, I am going to run the regression equation. We are getting regression output. You see that the intercept is 60. The intercept of the student underscore population variable is 5. So we can write it y equal to 60 plus 5 x1. Here x1 is student population. Then we can see that this p value also, it is less than 0.05. So this independent variable is significant values. You see that r square is 0.903. That means 90.3% of the variability of y is explained with the help of this regression model. Similarly, for the x coefficient, the standard error is 0.58. Now we are going to get the ANOVA table for this regression. So this ANOVA table, type this print ANOVA underscore LM fit1, we are getting this ANOVA table for the regression analysis. What we are understanding here, for independent variable is student population. So the degrees of freedom is 1, sum of square is 14,200. When you divide this 14,200 divided by 1, we are getting the mean sum of square. Then for error term, the degrees of freedom is 8. How it is 8? Because there was a 10 data set. So the degrees of freedom is 10 minus 1 minus number of independent variables. So 10 minus 1, 9 minus 1, 1 independent variable, so 8. So the sum of square is 1530. So when you divide this 1530 divided by 8, you are getting the mean error sum of square. So f value is this 14,200 divided by 191, you are getting this one. So p value is very low, this model is valid. Next, what we are going to do, we are going to draw the residual plot. In x axis, I have taken the student population, that is independent variable. In y axis, this is not the sales, it is the residual for the sales. See that. Next one, we will see the studentized residual plot. You run this. So this is your standardized residuals. So we will plot this standardized residuals. So this is a standardized residual. So what is the interpretation from this is, all the points are between +2 and -2. So we can say this assumption is valid. Next we will go for checking the normality of the error term. So now what is happening, we are getting the QQ plot when you run this code. So this QQ plot says that all the points are around this red line. We can say this model is, that is the assumption of the normality is tested, it is correct. In every lectures, you can follow this code, you can verify this output. I will also planning to share these codes with you when you register this course. Now I will conclude what we have seen in this lecture. In this lecture, we have tested various assumptions about the regression models. These assumptions we have tested with the help of different residual plots. We have seen 4 types of residual plot. One plot is residuals against independent variable. The next one is residual against our predicted values. The third one is standardized residual plot. The fourth one is the normal probability plot. So these different graphs helped us to test the assumption about the regression models. The next class we will discuss about the multiple regression models with some other examples. Thank you.